This is the story of how stochastic systems met signal-temporal logic. Robots are becoming more capable and increasingly incorporated into our lives. With this increased incorporation, safety becomes a major concern. This begs two questions. How do we express safety, along with the robot's other objectives? Also, how can we ensure robust satisfaction of such expressions? For question 1, a popular way is to use temporal logics because we can make guarantees and verify that a robot satisfies the specifications. Linear temporal logic lets us specify objectives in discrete time, but doesn't allow for continuous time-dependent considerations. For example, you couldn't specify that you don't want your vehicle stopped on train tracks for more than 2 seconds. Signal temporal logic, or STL, is a variant of temporal logic that allows us to incorporate such continuous time considerations. Consider a robotic vacuum that must return to the charging station within 10 minutes. Also, if it traverses through a puddle, it must stay away from the charger until drying off on the carpet within 3 minutes. One satisfying trajectory might go through the puddle, but then dry off on the carpet before making its way to the charger. Another trajectory might instead choose to avoid the puddle entirely on its way to the charger. We might initially prefer the second trajectory because it seems simpler and safer to avoid the puddle. However, real-world applications of such systems are subject to stochastic disturbances, and so these trajectories are more accurately captured by these uncertainty ellipses. It's now evident that the second trajectory is quite likely to go through the puddle and into the charger, which is precisely the unsafe behavior we want to avoid. This is why we wish to ensure robust satisfaction. This work proposes a novel robustness measure that quantifies the difference in these trajectories, a monitor for the measure that lets us reason about trajectories as they evolve, and a motion planner that uses this monitor to find safe motion plans. To develop some intuition on how a robustness measure should work, consider this environment, this belief trajectory, and the specification eventually reach goal. We only need one point on the trajectory to be in the goal, and so we can characterize the satisfaction by this point. In other words, we care about the point with the maximum probability of being in the goal. Alternatively, consider the specification always avoid obstacle. Now, we're reasoning about all points in the trajectory, not just one. However, we reason that a chain is only as strong as its weakest link, and so we can still characterize the satisfaction by one point, this point. We care about the point with the minimum probability of avoiding the obstacle. Let's take a closer look at this probability. We are using signal temporal logic, which reasons about linear predicates, so the obstacle and goal are actually composed of these predicates. While it's straightforward to reason about the probability of A or the probability of B, using these to draw conclusions about the probability of A and B is not so clear. We can, however, bound this probability, and intervals such as these are crucial to accurately reason about the satisfaction of such properties. These intervals are the foundation for the stochastic robustness interval, an interval between 0 and 1, also known as the story. The stochastic robustness measure itself is the lower bound of the story and is also called the storm. The story is defined recursively with respect to the semantics of STL and probability theory. For a more in-depth discussion of the mathematics, please refer to the paper. Consider the environment from before with the specification avoid the obstacle until reaching the goal within 6 seconds. One trajectory might look like this, or, if subject to more uncertainty, look like this. Notice that both bounds of the story are lower for the more uncertain trajectory. One important property of the measure is that a storm of 1 means that all realizations of the trajectory satisfied the specification. Similarly, a story upper bound of 0 means that all realizations violate the specification. While this shows that the measure correctly captures and quantifies the satisfaction or robustness, the true capabilities of the measure come from quantifying the robustness of evolving trajectories. The story monitor is an interval that subsumes the story and can reason about future possibilities. Consider this partial trajectory, which might go on to evolve in many different ways. This theorem states that if you find the story monitor at this point and the story of each of the trajectories, the story monitor will subsume each of the stories. This property lets us reason about how good a trajectory might be in the future. Based on this, we propose a meta-algorithm that can turn any sampling-based tree search into a robust STL motion planner. Consider a typical sampling-based tree search algorithm. When sampling a control input, you get a new partial trajectory. You can use the story monitor to see the highest possible storm this partial trajectory could result in and reject the new branch if it's too low. Promising branches will have a high upper bound for the monitor and stay in the tree. We can also assume trajectories are complete to calculate the storm directly. If a branch has a high enough storm, then the solution has been found. We can even go as far as to take the robustness of the found solution and plan again with that as the new threshold, and this lets us optimize for robustness. Experimental results have been very promising. This figure experimentally confirms that, on average, the motion planner will asymptotically optimize for the robustness measure. We also simulate the motion plans for these stochastic systems to find the statistical rate that these motion plans result in satisfying trajectories. We see that trajectories with a higher storm are statistically more likely to satisfy the specification, and this holds for a variety of STL formulas. These two experiments together imply some very exciting capabilities, and we think that's a story worth telling.